recall, we had two main types of variables at the beginning of the semester. Those types of variables were quantitative or numerical, and the second type was categorical. Now we're going to focus on specifically the first type, quantitative, and we're going to break that down even further. So make a highlight or a note here, types of quantitative variables or numerical variables, and we're going to break that down into two categories. The first one we'll call discrete, and when we mean discrete variables, they're numerical because we're under the quantitative umbrella, and discrete variables are ones where they're defined by distinct points on the number line, and they're typically counting numbers. So say distinct points on the number line. And again, if you want kind of a one-word way to think of this or remember it, you can think of it as counts. And maybe an example of this might be something like, I don't know, number of siblings that a person has, maybe number of days until some big event for a countdown, things like that. So distinct points on a number line, nothing with like decimals or something like that. That's going to be our next type. Are continuous quantitative variables. And by continuous, we mean it could occur anywhere on a number line. So between 3 and 4, I've got lots of options. 3.01, 3.011, 3.01111, so on. So that's what we mean by continuous. It could be anywhere on a number line. And if you want a one-word definition to remember this, think of things that are usually measured. Now I know in real life we're kind of limited by the precision of our instrument, but think of height. You know, it's not just 6 feet. We could measure that to some greater detail there. So usually things that are measured. So for example, weight of an object, concentration of some chemical, and so on. So anything that can be measured more precisely rather than just distinct counting points on the number line. So for right now, we're going to focus on discrete variables, and later on we'll talk about a specific type of continuous variable. But for the moment, let's focus on discrete. And the next definition should sound kind of familiar. A discrete probability distribution is going to give two pieces of information. One, our possible outcomes, and two, the probability of observing each one. So this might sound kind of like the data distribution, except we don't need data to come up with this discrete probability distribution. And just as a side note, if we add up all the probabilities of all possible outcomes, we should get 1, meaning it represents 100% of the possibilities in that particular experiment or distribution. So let's start with a really simple kind of textbooky example. We want the probability distribution for rolling a fair die once. So we need those two pieces of information. 1, the possible outcomes, and 2, the probability of observing each. So the first row I'm going to label X, my possible outcomes. Now remember, we're talking about discrete distributions, so these need to be distinct points on the number line. Well, if I'm rolling a fair die, I can get 1, 2, 3, 4, 5, or 6. And then I also need the probability of observing each. So the probability of X, or of that particular outcome, if I'm rolling a fair die, keyword there, then they're all equally likely with probability 1/6. So that's what we mean by probability distribution for a discrete variable. And you'll notice if I add up all those probabilities, I do in fact get 1, meaning they represent all possible outcomes. Okay, so we've got our probability distribution for a discrete quantitative variable. Now, let's tack on another vocab word here, this idea of the expected value. Now, think of expected value as just a fancy word for the mean or average of this distribution. So, as a little side note here, if you recall, for data, we had the mean, we used the notation x bar, and we said that was add up all the data points and divide by how many you have. Well, we're again not necessarily using data to calculate this. This is more of a theoretical mean. If we rolled the die many times, what would we expect the average face value to be? So this is kind of what we expect without actually collecting the data, more on a theoretical type probability. So in this case, instead of using x bar that we use for data, we're going to use mu to be the mean for this whole population. And it's going to start off the same way. We're going to add up our observations, or our possible outcomes, but I don't have an n, how many I've added up, because I'm not collecting data here. I'm going to weight each of these by the probability of actually observing that outcome. So it's just a weighted average of the outcomes times the likelihood of seeing each of those. So I'll box this formula for us here, and let's check that out in the context of our example. So it's asking for the expected value, so that's our key phrase here. We want mu, this theoretical mean or average or expected value, and we're going to find that by considering our possible outcomes. So I could see a 1, so that's my first x or outcome. I'm going to weight it by the likelihood of observing that, which is 1/6. I'll see a 1 1/6 of the time. I'll see a 2 1/6 of the time. And I'm just going to add this up across the board here. And if you do this, you should get, I guess I'll fix that for you guys. You should get 3.5. And if you think about it, 3.5 makes perfect sense, because looking at our data distribution, we have, these are our outcomes. They're all equally likely, so our mean or our balance point should be right here between 3 and 4, or 3.5. So what this value is telling us is, if we roll the die, notice we calculated this without any data. All this was theoretical. If we roll the die many times, we would expect, kind of part of the definition here, expected value, would expect the average face value to be 3.5. Now, one last comment here. You might say, okay, this is 3.5, but there's no 3.5 on the sides of the die. That's totally fine. Make sure you do not round it. Leave it as is. This is talking about an average behavior, so that can certainly have decimals. We're not saying it's required to be one of the particular observations, but an average of those. All right, let's try one more in a slightly different context. So here we're looking at New York and looking at the population in the prison and the general population and comparing levels of education. And this is really important because they're considering offering degree programs in the prison population, so they have more opportunities once leaving prison. So we have these two tables. The first one is our prison population, the second one is the general population. And to see kind of a difference of the discrepancy here, let's go through and take a look at these questions. So the first one, what percent of the prison population has 8 years of education? Or in other words, find this value that was left blank. So I'm going to start using our probability notation here. So probability X, the years of education. I'm going to put a little P subscript every time I'm talking about prison population, G if I'm talking about general population. So find the probability that X, the years of education for the prison population, is 8. So think about what we mentioned earlier. We have our list of possible outcomes and the probability of each. And we know that if we add all these probabilities up, we should get 1. So it should be easy to find this value. We'll just figure out the leftover. So 1 minus all of these other values. And working that out, you're going to get 0.142. So about 14% of the population, the prison population, has 8 years of education. Alrighty, let's check out some of the other questions. So next one, what percent of the general population has at least 12 years of education? Same question for the prison population. So I'll again use those subscripts to help us here. When it says at least, make sure you know at least means at minimum 12 or more than 12. So the years of education for prison is greater than or equal to 12. And then it also wants us to answer the same question for the general population. And then we might get a feeling for the discrepancy in these two groups. So to answer it for our first group, all you need to do is add up the probabilities that are 12 or more, or at least 12. For this one, you're going to get a value of 0.403. And then on your own, try the next one for a moment, again for comparison. Same question on the general population. Okay, hopefully you're getting a number about twice as large here. So you can see there's a huge inequity here. 40% of the prison population has this higher level of education compared to over 80% in the general population. So a very big difference in inequity in these two groups. Next part, it's asking about the expected number of years of education. So this should be your keyword that stands out here, the expected. And in your mind, we just talked about that. You should think that's a fancy word for average. So we're going to use that symbol mu. And we're talking about the prison population. So this is our weighted average. We're not going to go collect data. We're going to use this information available to us. So the first value I can observe is 8 years of education. And I see that 14.2% of the time. So my first term is 8. And I see that 14.2% of the time. Write it as a decimal though. So that's my outcome. I'm weighting it by how likely I am to observe that. Then the next one, 10 years of education. I'm going to see that almost half of the time, 0.455. So 10 years of education, and I see that most often, almost half the time. And we're going to keep doing that as we go across to 16 years of education, and we see that 2.4% of the time. Okay, before putting that in your calculator and working it out, again, these dot dot dots fill in the other years of education there. I just didn't want to write them all down. But before figuring out what our final answer is, let's look back up at the distribution and see if we have a general idea of what makes sense. So looking at this tells us 16 years of education is not very common. 10 and 12 are most common. So I'm probably going to see an average or an expected value somewhere between 10 and 12, probably closer to the 10 side of things, since over half of our observations have 10 years of education. So if you want to pause, try it on your calculator. When you do, I got 10.798 years of education. Again, the decimal may be strange to you. Don't worry about it. We're talking about an average. And our answer makes sense. 10 occurred almost half the time, so our average should be around there. All right, on your own, try this last one, and then we'll check it together. Okay, hopefully you're noticing expected is telling us to find the average, and this time we're talking about the general population. So we're going to use the distribution for the general population. Same observations, 8 years to 16 years, but we have different percentages for each of these. And looking at this one to get a feel for our answer, we notice that 12 and 14 are the most likely values, so we would expect an average kind of in that ballpark, 12, 14, 16, so probably closer to the 14 side of things, but we expect our average to be a little bit higher than the previous example. So if you work that out, you've got 8 years of education, and in the general population, only about 7% of people had that. And again, if it's okay with you, I'm going to skip, do the same thing for all of them. The last term, 16 years of education, that happened 22% of the time. And you're going to get an expected value of 12.896 years of education. And just like we noticed for the percentages, a big discrepancy, we'll also notice this large inequity here in the expected value or the average years of education between these two different populations. So in this section, I just want to make sure you got all the important parts here. The first important part, you really need to know the distinction here between discrete and continuous variables. They're both quantitative. Discrete is a counting type, continuous is anywhere on a number line. The distribution, the probabilities have to add up to 1, so if you don't know one of these values, you could easily figure it out. And then also, make sure you know how to find the mean or expected value of a discrete distribution. And we saw that was just a weighted average, each outcome times its probability, and adding it up across the chart or across the distribution for all different outcomes.